Very well, so good afternoon, everyone. I am very excited to be here today. I'm going to be presenting Innovation Spurred, evidence from South Korea's big R&D push, which is my job market paper, and it's called to work with Chan Kim, who is a classmate at the University of Maryland. So the question that we ask in this paper is, how does innovation policy affect research output and economic outcomes? Naturally, we are not the first ones to ask this question. There are various literatures in different disciplines that provide governments with motives to intervene markets to address market failures. So what is more of an open question is what works and what doesn't, right? And in particular, in economics at least, there is very little literature on on large coordinated R&D programs. So what we do in this paper is we study the G7 program, which was South Korea's first mission-oriented R&D program. So this was a large program. It invested over $7 billion between 1992 and 2001 and mobilized over 100,000 researchers. The mission was to reach frontier level, G7 country level, hence the name, capabilities in selected technologies by the 2000s. So why did South Korean policymakers want to engage in this sort of adventure? Well, the thing is that they identified that they needed to compete in higher value-added markets, right? So by the early 1990s, South Korean exports essentially stagnated. And there is some consensus among South Korean economists that the reason behind that was that after the return to democracy in 1987, there was an explosion in labor costs. So in order to keep up competing, they needed to engage with different sorts of products or higher value added products, okay? Naturally, there are some hurdles along the way when one wants to do that. Essentially, there were two types of hurdles. In the case of technologies that had immediate commercial applications, like a high definition television or some specific type of semiconductor, the problem was that the research projects that needed to be implemented were too large and too risky for individual firms to pursue on their own. So there was a coordination failure, so to speak. There are technologies in which there were huge externalities, right? So you can think of a nuclear reactor that has very large national security and environmental externalities. So when that happens, there is this very large gap between the private return to R&D and the public return, right? So this is like a natural case of a suboptimal provision of a public good. So what the program did was to provide a research subsidy, which would solve those issues. There is nothing new there, I guess. What is special about this program is that the approach to project selection was centralized, and there were public research institutes that managed the projects on a daily basis. Okay, so this is not like a decentralized tax credit, for example, in which firms choose which technologies to pursue independently. It's the government telling them, we're going to engage with these projects, come over, right? So there was a unit that was created to run the program. It was named the G7 Program Unit, and it opened like a call for applications within the government, and ministries of all kinds presented 74 candidate projects. 23 were selected. Okay, of those 23 that were selected, only 18 were funded. Okay, and the reason for that was that after being selected, there was a budget shock that reduced the program's overall budget. So you're going to ask, okay, which were the projects, well, mega projects. So on the left, you're going to see the mega projects that were supported at the end. So you are going to see like very well-known like South Korean successes, like a flat panel display, a high definition television, and so on. And less known successes like a nuclear reactor, right? For example, today South Korea exports these nuclear technologies to the Middle East and now increasingly to Europe, right? And on the right-hand side, what you're going to see are the selected but unfunded mega projects. And later on, as I'm going to talk in more detail later, what we do, very high level, is we use these projects, as our treatment projects. And we're going to use these selected patent-funded mega projects as control projects. Okay? So specifically in the paper, what we do is we use newly digitized files from archival sources, patenting and export data to study how patenting and exports in program-targeted technological classes evolved between 1980 and 2015. I'm going to show you an example of what a technological class is precisely in a few slides, but you can think of it as a broad, very loosely speaking. Okay? We had two challenges when implementing this paper. The first one was a data challenge. So we have a lot of data on patenting exports, which we essentially download from the internet. There's nothing fancy there. But we were able to compile a lot of historical data, particularly program reports that detail each research project's activities, goals, and so on. Now, the problem is that these two things don't talk to each other. We have 6,000 pages of PDFs from one hand and a lot of CSV files in the other. So the way to make these two speak to each other, like many things these days, is a language model. Okay? And to address selection concerns, which are a salient concern in this type of policies, we use these mega projects that were selected but not funded. What we find is that by the 10th year after receiving program support, program-targeted technological classes doubled their quality weight patenting output and tripled their real exports relative to control classes. The dynamics of those effects are very different. So what we see is that there is like an increase in patenting that happens almost immediately after a technological class is supported. But for exports, we really find muted effects for 3 years. And we start like picking up some effects 5 years after a technological class was supported. So that's a lot, right? So then when we ask like about the economics and the mechanisms that are driving the program's effect, we find that technological classes with less concentrated scientific output before the program observe greater effects, which suggests that spillovers are an important driver of program effects. Then we will want to make a cost-benefit analysis, and we find a 21% internal rate of return and a cost-benefit ratio of 3.3, which implies that the program was a very cost-effective intervention. Conclude that the program shifted the direction in which the South Korean economy innovated, and this had important economic consequences. Okay? So the outcomes that we look at are future citation weight patenting. We do this because there are many patents that are probably useless. So the way in which the literature deals with quality is to weight every patent by the citation it gets. And we also look at exports. And we look at the country technological class level. Okay, so I'm going to show you both within Korea and across country evidence in a couple of slides. So we look at data between 1980 and 2015, and we get data from USPTO and UN Comtrade. So here's an example of technological class. So you're thinking of something like a car, like a motor vehicle. This is the level at which we look at patenting, and this is the level at which we look at exports, and that's just because of a data availability issue. Okay? When it comes to a treatment, as I was hinting at before, there is a wealth of textual information that we get for about 4,800 G7 program-related projects. So I showed you 23 mega projects. Each project had some like smaller research projects, right? So in total, we had 4,800, right? We got this through something like a Freedom of Information Act request. It was in a basement in South Korea's National Research Foundation, but we got it. And that was very exciting, but the problem is that we don't observe the technological class that was targeted by each research project. So that's a problem because we can't run econometrics, essentially, no? So the challenge is, okay, how do we map this textual information into technological classes? And the answer is a language model, okay? So what we do is we input each project's goal and description of activities. in this model that we didn't develop, that is called IPC-CAT, that was developed by the World International Patent Organization to help resource-constrained patent offices classify inventions into technological classes. So you can think of two PhD students as the most resource-constrained patent office in the planet, right? So we take advantage of this like technology, and what we get after we do this is a list of technological classes that relate to each project. So this is the typical record that we get. So this is for a network device. We get the project's name, the researchers, the firms involved, the time span of the project, the subsidies, the private contributions, and the description of activities. What we don't have here is a list with the technological class that each project targets. The language model gives us that. Okay? So when it comes to empirics, we exploit that high potential mega projects were selected but were not funded, right? And these projects went through the whole selection process. They were selected by the program experts, which used as an input a survey that was sent to experts in government and academia. But given the budget shock, they couldn't be supported. So what happened was that the South Korean government tried to fund these large projects, the aircraft, the high-speed maritime ship, the natural language processing technology, but it didn't find a way to do so. Okay, and so we find evidence that spawns our identification strategy. So as I'm going to show you in a few slides, there are no trends in patenting or exports. This means that targeted and controlled technological classes were performing pretty much, they had similar trends before the program targeted a technological class. I'm not going to show you the next two bullet points, just in the interest of time. But we find that targeting is not informative of underlying economic characteristics like capital intensity, output per worker, and so on. Like that's in the paper. If you want to talk more about it, come talk to me. And finally, our results do not change when we exclude superstar technological classes, right? So if we exclude like semiconductors, cars, like technological classes that were performing very well before the program, our baseline results do not change. Okay? And I'm going to show you results for Korea and across country. And as you're going to see, like results do not change much. Okay, so I'll go very briefly over the econometrics. First, I'm going to show you our outcomes. So it's going to be patenting. This is the inverse hyperbolic sign transformation, which is something that produces like how spanned is the data and this outcome, similar to a log transformation. And we're going to look every year at the change in patenting relative to the year before any technological class was supported. Okay, pretty much the same for the treatment. For exports is exactly the same thing. The only difference is that we look at 3-digit level technological classes, again, because of that data availability. So these are our main estimating equation. There is a summation that should be there somewhere, but essentially on the left, what you have is the inverse hyperbolic sign, the change in the IHS of patents in a given year after a technological class was supported relative to the year before it was supported by the program. On the right-hand side, you are going to see this variable here, which is the change in the treatment status, and is the one that I'm going to report. And we're going to control for some things. So there are some fixed effects that account for demand shocks, differential trends across sector that relax a bit, that could threaten like our identification strategy. And we also control for pre-existing patent insurers, okay? Just to make sure that we are not just picking up like some policymakers' preference for sectors that already patent a lot or export a lot. In the case of exports, it's pretty much the same thing. The only difference, again, is the level of aggregation at which we do the analysis. Here we are going to use, like in both cases, a local projection differences in difference approach, which is akin to the local projections method that Andrew talked about. So after all that, let me show you the results. So on the top panel, you're going to see patenting, right? So here to note is that first, there are no differential trends before the program. And once the program supports a technological class, patenting starts like going up and going up pretty quickly. So these point estimates imply that by the 10th year after a technological class was supported, patenting doubled in targeted classes relative to control classes. At the bottom, you're going to see exports. And here, as I was hinting at before, we really take a long time to pick up like effects, no? And I mean, that I think makes all the sense. Like, you patent a technology, you take it to a product line, you have to market it. Until all that happens, that typically takes a lot of time. What I think it's interesting and a bit concerning is that if you think of industrial policy and the political economy of industrial policy, is that it takes a lot of time to get the returns, right? So there is like a political economy problem because you support some sectors and you see the fruits of that. Well, you don't see the fruit of that, essentially. Now, if you are like for your presidential term, it's the person that takes office after you that is going to see the returns, right? So that's a problem. Okay, so then we use the cross-country sample. So this is pretty much the same empirical specification. The difference is that we have observations from many countries around the world, and we include a series of fixed effects at the country level that imply like a different point of comparison. Like in the previous set of results that I show you, the point of comparison were essentially these technological classes that were not supported at the end, right? Here, the point of comparison is, or are going to be, technological classes that were supported, but in other countries, okay? So we are sort of changing the comparison point and see how robust our results are to that. And what we find is that it's pretty much the same story. Like, there are very few differences in terms of point estimates. They're pretty much the same. I had to check 4 times that I was, not getting the same, the image from the previous slide here. But what this is telling us is that our results are robust to that change in point of comparison. Okay. So here is something about mechanisms. Okay, about the economics of the program. What we do here is we compute the citation shares for each technological class the 5 years before the program was active, right? So for example, if there's just one company patenting, say Samsung, that's going to be a very concentrated citation share, right? It's 100%. If there are more companies, the HHI is going to be lower. What we find is that the technological classes that had lower concentration, like a lower concentration index in terms of citation shares, did much better, right? Here I am reporting like changes for a 1 interquartile range change in the HHI, which is 6,380, which is a very large change. But the main point is that this differential effect is like 3/4 of the baseline program estimate. So what this is telling us is that knowledge networks before the program really were important. Okay, so that's I guess something useful for policymakers when designing this type of program. Okay, so I think that's in some sense a bit of a fairy tale so far, right? So what if these findings came at a huge cost, right? So even if these results are very large, if they're not much when you compare it to a cost. Maybe it's not like a very good idea to implement the program. What we do is to run a cost-benefit analysis, sort of a back-of-the-envelope calculation. Okay, so we're going to count benefits for 15 years after a technological class was targeted, and we are going to take a method from the literature to value patents. Okay, so what we do is first we get a number of program attributable patents from our reduced form estimates, and then we are going to get a patent valuation using this method, right? So what the method does essentially is to look at the stock market capitalization of a patent grantee after it's official that it has been granted a patent, right? And that is a market-based estimate of the value of the patent, right? And we adjust, of course, for market benchmark returns, and that gives us a patent value for every patent related to a publicly traded South Korean company, okay? And this is using South Korean stock market data. Once we have that, we compute the median of patent valuations for each treated technological class every year, right? And when we multiply the results from those previous two steps, we get a Korean won valuation of those program benefits, okay? So we include some costs, right? So first, there are the R&D expenditures. So we observe that directly from the program files I showed you before, and we include opportunity costs, okay? And for government expenditures, we assume that the South Korean government could have spent that money in higher education, right? And the social return to higher education in South Korea, according to the literature, in the 1990s was 7.5% per year. And for the private contributions, we compute a measure of return on equity, and we assume that that private investment would accrue that benefit. That is like 9% per year. Okay, we take all the values to Korean won and discount them using a 5% discount rate. And what we find is that the benefits were 3.3 times the costs, and the internal rate of return was 21%. Okay, so the program was a highly cost-effective intervention. Okay, so we conclude that the program shifted the direction in which the South Korean economy innovated. There was a large persistent impact on quality weight patenting. The effects were very quick and were larger in technological classes that had less concentration in terms of scientific production. That shift had a relevant impact on the real economy. However, those effects took some time to materialize, right? So remember, we don't find any effect 3 years after after a technological class was supported. And it was, at the end of the day, a highly cost-effective intervention, right? So benefits were more than 3 times the cost, and internal rate of return, roughly 21%.
Thank you so much, Luis. Very, very quickly, one quick question. I'll let you. Looks like we have a candidate here.
Yeah, I think actually you're underestimating the effect quite a bit, because you're looking at the value of patenting, which is not the same as the value of the innovation. From the private side, you're missing the value of, well, the non-patented innovation, which would already have been put potentially in the value of the firm. And of course, you're also missing the social, the additional social benefit that you may have. So the returns are probably much, much higher.
Right, so yeah, so this was intended to be sort of a lower bound, no? Yeah, absolutely. So, given the estimates that we get, we internalize the within sector externalities. That's in what we get, but we are sort of muting the across sector spillovers. Yeah, absolutely.
I mean, I would say that's correct, except there's also a business dealing effect. that comes in, and so that could, it could be that this patent just allows that firm maybe to get epsilon better than some other firm and steal its business. So we can't really say from the stock return whether it's an over or an underestimate, I would think.
Mhm.